How do we transmit electricity efficiently? Because we don't live near power generating stations. And how do we get a safe level of electricity into our homes? This lesson is on the transmission of electrical energy. So, since electrical devices need energy, we need to be able to move that energy from one location to another. Also, most of the electrical devices that we use in our house have a power rating. So, this tells us the energy consumed per second. And that power rating is determined by taking energy and dividing it by the time that that device would be used in seconds. So, power rating describes the maximum safe input of electricity to a device. So, we can work through several equations and at the end get power is equal to current time multiplied by voltage. So, power in watts is measured by multiplying the current and the voltage. So, looking at a set of speakers, which is an AC device, so it only works if the current changes direction. Now, a coil supplies the resistance to this circuit. So, we want to calculate the voltage applied across the speaker when the resistance is 4 amps and the current is 2 amps. So, voltage is equal to current times resistance, which is equal to 2.00 amps times 4.0 ohms, which gives us a total of 8.0 volts. Now, let's calculate the power consumed by the speaker. So if power is equal to current times voltage, this is going to be equal to 2.00 amps times 8.0 volts, which gives us a total of 16.0 watts. 16.0 watts. So in many cases, power needs to be calculated, but we don't know the voltage. So then we have the following formula. Power is equal to current squared multiplied by resistance. And again, this formula is in your data booklet. So in that same speaker in the car, we're going to turn the volume up. So we have now a 4 ohm resistor and 4.5 amps of alternating current flows into the speaker. So this is not a car speaker, this is a house speaker. So I'm going to take my formula. That is power is equal to current squared multiplied by R. And we get 4.50 amps squared multiplied by 4.0 ohms. And we get a total of 81.0 watts. So a lot more watts once we've turned up the volume in that speaker. Now, common to most households is an electrical bill. And energy companies bill you for electricity through the use of a power meter so they can see how much you've consumed. And this is measured in kilowatt hours. So the formula that we use to determine energy is equal to power multiplied by time, but time is in seconds, so we have to do some conversion here. Now, just for a fun tip, Las Vegas uses about 400,000 kilowatt hours per year for a total cost of $40 million. So we're going to do a kilowatt hour calculation for a lava lamp that operates at 100 watts a week for 60 minutes. So we want to calculate the energy consumed in kilowatt hours. So 1,000 watts is equal to 1 kilowatt. 60 minutes is equal to 1 hour. So we have about 1 kilowatt hour consumed per week in that lava lamp. Now we want to calculate the energy that is consumed in joules. So we're going to take energy is equal to power multiplied by time. So we're going to take 1,000 watts, multiply this by 60 minutes, by 60 seconds, and we get a total of 3.6 times 10 to the 6 joules. Okay. So that's how much energy is used in joules using this lava lamp. So now I want to see how much does it cost to run this lava lamp 60 minutes a day for a year. So I'm just going to erase this so that I have room. So we calculated before, we have 1 kilowatt hour per week that we ran this lamp. So now we take 1 kilowatt hour per week, multiply it by 52 weeks in the year, multiply it by the cost of electricity, and I'm going to put this into $0.093, so I don't have to convert my cents. And we get a total of $4.84 to operate this lava lamp for 1 hour a week. So when we look at power transmission, again, our formula is current times voltage. And to transmit lots of power, we either need to have a high amount of voltage or a high amount of current. High voltage is dangerous, but if the current is too high in power lines, lots of that electrical energy is lost as heat. So to transmit power efficiently, we need to use unsafe high voltages. So we're going to use alternating current so that we can use transformers. And so that's one advantage of using alternating current is we can transform it, which is step down the voltage to a safe level before the electricity enters the home. So our power gets to our house after it is created at a power generating station. So in Alberta, often that's a coal power generating station. The transformer at the power generating station is going to step up the voltage so it can be efficiently carried long distances. And then when it comes near to your house, they'll go through another transformer, which steps the voltage down to a lower level. And then even right at your house, there's another transformer that steps it down to even lower level before it enters your home. Now these transformers are coils, are blocks surrounded by coils of wire. So we have the primary coil, which receives the input voltage from the source, and the current and voltage remain in the coil because it's isolated. But then we have a secondary coil that creates output current and voltage. The primary and secondary coils are not connected, and the secondary coil is affected only if the current is changing, which is why we need that alternating current. So transformers can change the voltage of an electrical current supply by stepping it up, which would increase it, or stepping it down and decreasing it. And now this happens before electricity enters your house. Step up transformers have more secondary coils than primary coils, and step down transformers have fewer secondary coils than primary coils. Now our transformer equations are all in our data booklet on page 3. And so one of them is the number of coils on the primary divided by the number of coils on the secondary is equal to the voltage on the primary divided by the voltage of the secondary. So whenever we're doing these transformer questions, we always end up in a cross multiply and divide situation. So what we can see in this one, because as our voltage goes down, our amperage goes up, and if our amperage goes down, our voltage goes up, is that the power stays the same through these transformers, which is why it's a very efficient way to send energy. So we're going to look at a couple transformer questions. And again, these formulas are in your data booklet. So a transformer has 50 primary coils. And 72 secondary coils. Now, if the voltage going to the transformer is 2,250 volts, what is the voltage leaving the transformer? So I'm going to put in my formula, NP erase that. Primary over the number of turns secondary is equal to the voltage primary divided by voltage secondary, which is what we're looking for. So I end up with voltage secondary. I'm going to put my numbers in first, actually. So I end up with 50 divided by 72 is equal to 2,250 divided by the primary voltage. So if you're good at cross multiplying and divide, you can go here, but I'll rearrange it for those of you who like to see that done visually. So primary voltage is equal to 2,250 times 72 divided by 50. So our primary voltage, or secondary voltage, sorry. That's supposed to be a secondary. So our secondary voltage comes out at 324 volts. So we can see how much it has stepped down from that 2,250 to be 324 volts. Okay, now a second question. If the current leaving the transformer is 50 amps, what was the current as it entered the transformer? So we can look at those formulas in our data booklet. So our primary turns divided by our secondary turns is equal to the secondary current divided by the primary current. So we have 50 divided by 72 is equal to 50 divided by the primary current. So we rearrange this. The primary current is equal to 50 times 72 divided by 50. So we get a total of 72 amps was our primary current. So in these ideal transformers, no energy is lost. And we have three different ratios that we could use. Number of turns and voltage, number of turns and current, and the voltage and the current.